Hi, welcome to this section of the Calculus Derivative Tutor. And this section we're going to switch gears a little bit and we're going to talk about how to take the derivatives of the trigonometric functions. If you haven't already figured it out, trig and calculus go hand in hand. And I'll tell you, after doing this for many years, the most common reason why people really have problems with calculus, number one, is if they're weak in algebra. And the second most common reason is if they're weak in trigonometry, because trig is really so prevalent throughout calculus. You're constantly using sine, you're constantly using cotangent and cosine. Definitely in calculus 1, even more in calculus 2, that you just have to be good at it. And that's why I created the trigonometry and pre-calculus tutor, to help people come up to speed there. So if you feel like you're a little rusty in your trig, if you feel like you kind of know what they are, but you should know them a little bit better, then please do yourself a favor and study your trig. You can do that with a book, you can do that with a DVD. It doesn't matter, but make sure it's done. So in this section, we're going to start to introduce and integrate trigonometry into calculus. And what you're going to find from here on out through the rest of calculus 1, 2, 3, differential equations, and every math course beyond it, trig is going to be everywhere. And what I mean by the trigonometric functions, they're mainly the 6 functions that we learn about: sine, cosine, tangent, cotangent, secant, and cosecant. Those are the 6. And the way I'm going to do this here is I'm really going to write the derivatives down of all 6 of these guys. And then we're going to do a series of problems to kind of show you how to use that knowledge to take derivatives of more complicated functions. So let's go ahead and do that right now. The 6 main trigonometric functions, like we've said, is, for instance, sine. All right, so I'm going to take the derivative of sine. I'm going to write this down in a different color. I think it'll be easier. The derivative of sine, and let me actually be a little bit more clear. When I say the derivative of sine, I'm talking about sine of x, or it could be sine of theta. A lot of times you take physics and you're talking about real angles, you talk about theta. Theta is just a variable. It's just like x or y or t or anything. So don't worry about what's here, but just know that you're taking the sine of something. If you take the derivative of sine, then what you're going to get back is the cosine function. So the derivative of the sine is the cosine function. And in the Calculus 1 tutor, sort of the companion to this disc, I actually graph the sine function and graph the cosine function and show you that the cosine function is really just a shifted version of the sine function. In fact, sine and cosine, they look the same. They have the same exact shape. It's just that cosine is shifted a little bit with respect to sine. So that if you were to look at the sine function and figure out the places where it is most steep, which means its derivative is greatest, the fastest part of the sine function is going to line up exactly where the cosine function has a maximum. That's why it is the derivative, because it describes the slope of the sine function everywhere. All right, so there's more of a discussion on that in the other Calculus 1 tutor, but for the purpose of this DVD, we're really concerned about getting good at taking derivatives. So the derivative of sine is cosine. The derivative of cosine is negative sine of x, right? So it's not the sine, it's the negative of it. So it's a slightly modified version of sine, but if you plot this and you plot its derivative, you would find out that it would be exactly equal to negative sine. Let me go ahead and write the rest of these guys down. We'll have tangent. We'll have, let me make sure I put the x here, tangent of x. We have the cotangent written as COT of x, and then you have the secant function, and then you have the cosecant function, which is CSC. Okay? Now, if I'm going to take the derivative of the tangent function, actually, let me put my little derivative marks for all of these guys. If I'm going to take the derivative of my tangent function, I'm going to get secant squared x. If I take the derivative of the cotangent function, I'm going to have negative cosecant squared x. If I take the derivative of secant, I'm going to have tangent x times secant x. And if I take the derivative of cosecant, I'm going to have negative cotangent, let me write the x here, cotangent x times cosecant x. Ultimately, ladies and gentlemen, you will have to memorize all 6 of these. I really hate telling you to do that because I don't like just telling people to memorize things, but it's kind of like memorizing pi. We all know it's 3.14. We know there's some more decimals after it, but we know roughly what it's equal to. We use it so much. Calculus is just chock full of trigonometry. You're going to have to remember the chain rule. Later on when we get to that, you're going to have to learn the product rule. We talked about that. The quotient rule. You're going to have to memorize these 6 derivatives because they're kind of fundamental. All right, so the derivative of sine is cosine. Derivative of cosine is negative sine. Derivative of tangent is secant squared. Derivative of cotangent is negative cosecant squared. Derivative of secant is tangent times secant. Derivative of cosecant is negative cotangent times cosecant. And I don't think I really have to tell you too much that the symmetry is just all over the place here. These guys are symmetrical because of sine and cosine. Tangent derivative is secant. The cotangent derivative is the cosecant with a negative, so there's kind of a symmetry there. Secant is tangent times secant, okay? Cosecant's negative cotangent times cosecant. So you can kind of read the symmetry in here. We have negative here, here, and here, and then these guys, when I pair them up this way, you can just sort of see the symmetry there. So it won't take too long for you to just say these over and over and over and over again. Program them in your calculator, whatever you have to do to go ahead and show that is true. And for every one of these, don't forget what you're saying. What you're saying is if I plot the cosecant function and get a graph, right? And if I plot this and get a graph underneath it, let's say, then the graph of the derivative is going to represent numerically the slope of the original curve at every point. So it's easier to look at an example up here. When I look at, if I plot the cosine function, the points where cosine is a maximum is going to be exactly where the sine function is going up in the steepest manner, where its derivative is a maximum. And so look at a few graphs, plot these guys if you need to understand that. But ultimately, you can plot them until you're blue in the face. But ultimately, on your exams, you're probably not going to be asked to plot these functions. You're probably not going to be asked to just regurgitate and put it down on paper what these derivatives are. You're going to be asked questions like the following. This is a great first question. Show that the following is true. Secant x derivative is equal to tangent secant. All right, so you might be asked to show that. It's given in the little table above, but how do you prove it, right? You're very, very, very likely to be asked to show that's the case. And even if you're not asked to be shown that is the case on a test, it's a great way to flex your muscles and make sure you understand this stuff. Now, I lied to you a little bit. When I told you these six trig functions were fundamental and that they were, these derivatives were fundamental and you had to memorize them, I kind of led you to believe that they were unique and you couldn't derive them, but that's not totally true. Really and truly, the true fundamental ones on this list are these two, the sine and the cosine. All of the other ones can really be derived if you know the answer to this question, to these two derivatives here. So really, if I cover all this up and say only give you these two, that's really honestly sufficient. But all calculus books are going to list all 6 of them, so I'm listing all 6 of them to you. All I'm saying is that you should be able to prove all of these are true. Now, how do we do that? The first thing you have to do, because we have a secant here, we're trying to take the derivative of secant x derivative. The first thing to do when you're dealing with secant or cotangent, or even tangent really, is you need to write it in terms of the fundamental trig functions. Don't forget all of the trig function, the trig function rainbow I like to call it. This is what I teach in the trig and pre-cal DVD. If you write them down like this, sine, cosine, tangent, cotangent, secant, cosecant, which is naturally the way that I remember them in my head. If you remember them in this order and write them down in this order, draw yourself a little rainbow like this. So you can see that sine kind of goes with cosecant, cosine kind of goes with secant, tangent kind of goes with cotangent. What this rainbow is telling you is, for instance, secant, which is tied to cosine. Secant is 1 over cosine. Cosecant is 1 over sine. Cotangent is 1 over tangent. That is what this little mnemonic does for you. It tells you those fundamental identities that you'll find in any trig book without actually having to memorize them. All you have to do is write them down in order. Sine, cosine, tangent. Cotangent, secant, cosecant. Draw the rainbow, you'll immediately know how to write them. So the reason it's important is because dealing with secant is difficult, But when you rewrite it in terms of what it's equal to, 1 over cosine x, now it's suddenly not so hard. Because I'm dealing now with a function that's one of the fundamental functions. I told you, sine and cosine are kind of like the fundamental functions. Tangent can be written as sine over cosine, so it's in terms of these guys. And all the other ones, are, as part of the rainbow, they're all written in terms of the first guys. So really, sine and cosine are the truly fundamental ones. These other guys are just in terms of them. So how would I take this derivative? You might say, well, I don't know. You never taught me how to do that. But you can use the quotient rule. We just used the quotient rule. Just in the last section, we have 1 divided by something. So let's use that quotient rule. Bottom times the derivative of the top, cosine of x, times the derivative of the top, which is just 1 with a derivative, minus the top, which is just a 1, times the derivative of the bottom, cosine x, take its derivative, over the bottom squared, cosine squared x, like this. And now's a good time to make sure that you understand. When I write cosine squared x, what I'm really writing is cosine of x squared. If you write the square just after the trigonometric word, right, like elevated like this, and then with the variable after it, it means that you're taking the whole thing and you're squaring it. That's what that notation means. And you're going to see it all through calculus. So make sure when I write cosecant squared, secant squared, when I write that stuff, it means secant times secant. It means negative cosecant times cosecant. That's what that means. All right, so let's continue on here. So what we'll have is cosine. What is the derivative of 1? Well, that's just 0. So we'll just leave it like that. Next, we have 1 times. What is the derivative of cosine? We go back to our table. Derivative of cosine is negative sine. So we say negative sine of x. All right? And on the bottom, we're going to have cosine squared x. All right, so let's simplify that here. So what we're going to have on the top is negative times negative is positive. So we'll have sine of x over. On the bottom, we'll have cosine squared of x. But what we're trying to prove is that the derivative of the secant function is tangent times secant. But what we've arrived at is this. And if you give up now, you might say, well, I'm not sure. I don't have any idea how it could come up like that. But just try to play with it a little bit. In this case, if you rewrite it, what you'll have is sine of x over cosine of x times 1 over cosine of x. Would you agree that this is the same thing? These are multiplied together, so you have sine on the top, cosine squared on the bottom. But everybody knows sine over cosine is simply tangent of x. Right? And then if you look back, what is 1 over cosine? If you look back to your trig rainbow, 1 over cosine is the secant function. So this can be written as secant of x. So we have proven that the derivative of the secant function is tangent times secant, which is exactly what this table tells us is the case. But notice that we really don't need it listed in this table. We can derive it for ourselves every time. So honestly and truthfully, if you forget these things entirely, you can derive them. However, it does take time. So I do recommend that you do memorize those, all 6 of them. But just know that they're all derivable. And in fact, it's a very common test question for you to be asked to derive them because it shows that you know what you're doing. It shows that you know how to apply this guy. It shows that you know how to do the quotient rule. So it's the perfect thing. And it shows that you know that this can be derived in terms of the other guys. So we're going to do another one similar to that right now. Let's show that the derivative of the cotangent function is equal to the negative cosecant squared x, which is given in our table. Derivative of cotangent is negative cosecant squared. So all we're going to do is prove that. The first step is figuring out how to rewrite this. So we'll have cotangent of x, that's what we're taking the derivative of. How can I rewrite the cotangent function? It's 1 over the tangent function, right? That's what this trig rainbow is telling us, 1 over tangent x. Right? We're taking the derivative of that. And by the way, if this looks foreign or if you want more practice with that, you can find lots of extra examples and discussion of why this is the case in the Trig and Pre-Cal tutor. So if you don't already have that, go take a look at it. I'm certainly trying to give you everything you need here so you can conquer calculus, but a lot of people need a lot of extra foundational work, so make sure you get it if you think you do. All right, so we have it in terms of 1 over tangent, but that's not terribly helpful. I mean, we could proceed like that. I mean, we could, because we know what the derivative of tangent is, and that's fine, but I'm going to do it a different way. What is tangent equal to? Tangent is equal to sine of x over cosine of x, right? Right? So all I did is 1 over, tangent is sine over cosine, but if I have 1 over, then that's exactly the same thing as cosine of x over sine of x. So I could have sort of skipped this, but just so you know, 1 over tangent is equal to cosine over sine, and I'm just showing you the intermediate step. So now this is really easy because it's a quotient rule. I know the derivative of cosine, I know the derivative of sine. Those are the fundamental functions we talked about a minute ago. So let's go and do that. So what we're going to have, let me go ahead and write it again, cosine of x over sine of x, derivative. It's a quotient, so let's use quotient rule. Bottom, which is going to be sine of x, times the derivative of the top, cosine of x, derivative, minus the top, which is cosine of x, times the derivative of the bottom, which is the sine of x, derivative, over the bottom squared, sine squared x, which is just sine times sine. All right, we're ready to make some headway. On the top, we're going to have sine times this, so we'll have sine of x. What is the derivative of cosine? The derivative of cosine is negative sine. That's one you should have memorized. So I'm going to write negative sine of x right here, minus cosine of x right here. What is the derivative of sine? That's one you should definitely have memorized. Derivative of sine is just cosine. So I'm going to have cosine of x. And on the bottom, I'm just simply going to have sine squared x. So on the top, what do I have? Sine times sine is sine squared. Negative comes out front. Negative sine squared x. Here I'm going to have negative cosine squared x over sine squared x. Now you might be tempted to leave it like this or not know what to do next. That's pretty common. But work with me here. Let's factor out the negative 1. We'll take the negative 1. Then it'll be on the inside sine squared of x plus cosine squared x. And on the bottom, you'll just simply have this again, sine squared x. Now, if you have to remember one trig identity in all of trigonometry that's going to help you in calculus and beyond, just one, it's that sine squared of x plus cosine squared of x is always equal to 1. Always. Doesn't matter what x is. If you take sine squared of 3 plus cosine squared of 3, you're going to get 1. If you take sine squared of negative 4 plus cosine squared of negative 4, you're always going to get 1. Doesn't matter what value of x is. And that is the number one identity that you always have to remember. So what this is telling us, really, is this entire numerator is equal to 1. Really. So what we're going to have is this negative, let's put it out in front of the fraction, 1 on top, and then we'll have sine squared x. But don't forget, what are we trying to prove? We've gotten it pretty close. Derivative of cotangent negative cosecant squared, but we've gotten down to this. So what we really have is negative 1 over sine of x times sine of x, right? But look over here. The 1 over sine of x is equal to cosecant, right? So if you really want to be explicit, this is negative 1 over sine of x times 1 over sine of x. 1 over sine of x we said is cosecant, so what you're going to have is negative cosecant x times cosecant x, which is negative cosecant squared x. And so we've proven that the answer is true. The derivative of the cotangent function is negative cosecant squared. What we did is we rewrote it in terms of the fundamental functions, did the quotient rule, simplified the result, and outspits the answer that you've come to know and love. So you could go through this as an exercise if you wanted to. You could prove all of these remaining 4. All of these remaining 4 can be proved in terms of using quotient rule, using this trig rainbow to know how to rewrite everything, etc. So, a lot of people look at this and they say, ooh, nice trick, trig rainbow. It's not really a trick, that's the identity. It's just that it's an easy way to remember the identity. Okay, so our next problem is we're finally going to move out of the realm of proving things. Y is equal to cosine of x minus 2 times tangent of x. All right, so now that's a function, right? And we want to take its derivative. So dy dx is equal to. It's term by term, right? So we take the derivative of this and then the derivative of this. What is the derivative of cosine? Derivative of cosine, you should remember, is negative sine. So this one's easy, this first part, negative sine of x. All right, over here, the 2 is going to stay out front. What is the derivative of tangent? You should remember, derivative of tangent is secant squared. So this is simply secant squared of x. And that, my friends, is as simple as it gets. Very simple function, derivative of this, and you're just really using the table that I gave you. All right, let's do something a little more complicated, but really not a big deal. What if we have y is equal to x times cosecant of x, and we want to take the derivative of that guy. This is a little more complicated because we have two functions multiplied by one another, right? So we want to take the derivative. We have to use the product rule. This times the derivative of this plus this times the derivative of this. Let's write that out. First term times the derivative of the second term plus the second term times the derivative of the first term. Now let's take the derivatives. We'll have x times, what is the derivative of cosecant? Derivative of cosecant is negative cotangent times cosecant. From our table, negative cotangent times cosecant. Okay? Plus, here we have cosecant. What is the derivative of x? Just simply get 1. All right? So really, this is about it. So y prime is going to be equal to, we're going to have a negative sign here, so I know I'm going to have a negative. Let me just leave this in front. So we'll have cosecant x minus from here, x times cotangent of x times cosecant of x. Negative x times cotangent times cosecant of x, and that's the answer. So it's really using the product rule in addition to your knowledge of the trig functions to arrive at something like that. So again, it's not that hard. Let's go to something that'll take a little more paper to solve. What if we have y is equal to 2x, open paren, square root of x minus cotangent of x. All right, we want to solve that guy. Take its derivative, in other words. So we'll have y prime. So notice what we have here, big picture. We have a function out here times a function inside. So if we define this as a function and this as a function, we can use the product rule. So it might help you visualize that to put parentheses around that. So let's do it that way. You can do it lots of different ways, but I like to write it like that because it makes it a little bit easier to visualize. So first term, so we'll have 2x times the derivative of the second term. And also the second rule that I always give people, always rewrite radicals as fractions, exponents like that. Minus cotangent x, take its derivative. So first times the derivative of the second term plus the second term, x to the 1/2 minus cotangent of x times the derivative of the first term, which is just 2x, take its derivative. Okay, so y prime, what we'll have is 2x, open paren. Now we take the derivative of this guy. What is the derivative of this term? It's just going to follow the same rule, 1/2 x to the negative 1/2, because we subtract 1 off of the exponent. What is the derivative of cotangent? If we go back to our list, which you eventually should memorize, derivative of cotangent is negative cosecant squared. Negative cosecant squared. So when I'm going to have to make it clear, have the minus from here, then I'll have negative cosecant squared x. And you can manage your paper however you like. You could make this a positive, but it really makes it clear if you just keep it all straight. Plus, this term here, x to the 1/2 minus cotangent of x. What is the derivative of this? It's just simply 2. So we've really got the answer. That is the derivative. But obviously you're not going to get credit for leaving it like that. So what we'll have is y prime, 2x times 1/2 x to the negative 1/2 plus cosecant squared x plus x to the 1/2 minus, well actually to make it, well let's just go ahead and do it this way, cotangent of x times 2. I could have done this multiplication in this step, but just to show everything. Now let's go ahead and do the multiplication in both steps. Y prime. When we multiply this times this and this, what do we have? 2 times a half is just going to be 1, so it's going to disappear. So what we're going to have is 1 times x, and we're going to add these exponents. 1 minus a half, because these are the same base. So 1 plus a negative half, which is going to give me positive 1/2. So I'm just adding those exponents. Plus 2x times cosecant squared x. This takes care of this term right here, the first term. The second term is going to be this multiplication. So I'm going to have plus 2x to the 1/2 minus this guy right here, 2 cotangent of x. All right? So now we just simply simplify, right? So we have x to the 1/2 plus 2x to the 1/2. So we add those together and we're going to get 3x to the 1/2. Dot over that, because I've handled those guys. These I can't really do much with, so I'm just going to leave them there. 2x cosecant squared x minus 2 cotangent of x. Okay, and just to be polite about it, this is the answer, but since our original problem had radicals, we can rewrite this in terms of a radical symbol plus 2x cosecant squared x minus 2 cotangent x. And let's just make sure it's right. 3 times the square root of x plus 2x cosecant squared x minus 2 cotangent x, and that's it. So you see, it's not that hard. You just have to, the main thing you have to do is identify that this is a function times this being kind of a large looking function. Second thing is rewrite your radicals as exponents. The reason you do that is because when we take derivatives like we did here, it's easier for your brain to wrap around it if it's an exponent, because then it'll follow the same rule as taking the derivative of x cubed or x squared. We use the table that we provided to take these trig derivatives, and then the rest of it is just simplification and straight up algebra. You're just adding exponents and things like that. So that's a good introduction to trig derivatives. What are the trig identities? What are the derivatives of the 6 main trig functions? And also I wanted you to know that most of those things that you see in your book really can be derived from using the quotient rule, the product rule, some trig identities, and also the first 2 derivatives that we learned of sine and cosine. So practice these problems, get some good experience, make sure you're really good at it. The next section, we're going to continue working problems with trig derivatives, get a little more lengthy, but really not too much harder than what we have here. It's just mostly more simplification work and show you how to keep your work organized. Because believe me, it's 100% the name of the game. If you can keep your work organized, you're much less likely to make a mistake. So part of my goal here is to show you how I methodically lay everything out so that if you make a mistake, and you will, you'll be able to go back and say, I missed this guy, to carry it down, and you'll nail it. But if you skip those steps, if you combine the signs too early and too often, it's going to be really hard to find those errors.